Welcome back. So in this lesson, I'm going to introduce the final sort algorithm that I want you to know about, and that's called the quicksort. In this lesson, I'll describe how the quicksort works, and we'll have a little demonstration of it and discuss its advantages and disadvantages. The quicksort works in quite a different way than all the sorts that we have looked at so far. At the start of the function, we choose an item more or less at random to be the pivot. Many programmers choose either the first or the last item in the list. Remember, it's an unsorted list, so that could be any value. And then we go through the list comparing every item with the pivot value. This will result in a list that is divided into two partitions, the values that are smaller than the pivot and the values that are larger than the pivot. These need not be equal halves, so we're not splitting the list into two regular halves, but arbitrarily partitioning it into numbers that are values that are larger and smaller than this random pivot. So there's a big random value in how the quicksort works. And then we'll recursively repeat this process with smaller and smaller partitions of the list, some of which will be very small and some might be quite a bit larger. So let's go through that. Here's an example of a list that is not in sorted order, and I have arbitrarily chosen the first item in the list to be my pivot. So my pivot is E, so I'm going to partition the rest of the items in the list into two halves, those that are larger and smaller than E. I'm going to actually use more than one marker for this, so bear with. E is my partition. Now my marker will move up the list comparing each item with the partition. So the first with the pivot, the first item is D. That's clearly smaller than my pivot value, so it can stay in the first partition, and my marker continues on through the list. It's now at G. G is larger than the pivot value. It's for later in the alphabet, so it doesn't go into my partition. The marker moves on. A does go into my partition, so I swap it back, and now A is in my partition. J doesn't belong in the partition, it's larger than E, and my marker moves on to B. So I haven't finished yet, but let's just have a little look at what's happened. My marker is moving down the list. It only has to go down the list once. And I've got a part of the list at the start there, which is all the values that are smaller than my pivot value. And gradually I am moving smaller values down into that partition. Let's just carry on with it. So let's imagine that I've got to the end of the list. The marker's passed right down to the end of the list, and I've successfully partitioned all the values in my list into two broad categories. We call them partitions. Values that are bigger and smaller, bigger or smaller than the pivot value E. So all that remains to do is to move E into that middle position between the two partitions. A very easy way to do that is to swap it with the end value of the partition. So there it is, it's arrived in its final position. All the values to the left are smaller than the pivot value, and all the values to the right are larger. The pivot value is in its final position, so we can now sort the two partitions either side of the pivot value. But E, I've coloured it in blue to show that it is now, we're going to leave that alone. It is in its correct position. So this helps us to reduce our sort task each time because the pivot is in its final resting place. So E is now in its final position, and I won't need to include it in any further sorts. The remaining values are in two large partitions, values that are bigger and smaller than E. And now I can repeat, using recursion, I can repeat the quicksort on each of these partitions. So I'm going to partition the first half around C as the pivot, and I'm going to partition the second half around G as a partition. I'm calling them halves, but obviously they're not exact halves of the list. So once I've done that, C will be in the right position and G will be in the correct position, and most of my list is now sorted. Some of my remaining partitions have only got one item in, which means I don't need to do any more work with them, and I've got a couple of small lists that will need another round of sorting. So it's actually quite a fast way of doing it, because every time we partition the list, we remove another item from our list of sorting values that need sorting. Some of our partitions are down to one item and they won't need sorting. So after a few goes through, the list starts to get into a sorted order. However, you will have noticed that there's a very large random element in all of this. And a lot of it depends on whether we've got a good value for the pivot or not. If the pivot is a value roughly in the middle of the list, then it all proceeds very smoothly. So we can act out the quicksort in class, choose one of the students to be the pivot, everybody else go to either side of him or her, and then repeat that with each of the partitions. So it's quite a fun activity in class. Okay, so that's the quicksort. We haven't programmed it, but that's an overview of how it works. It's usually quite fast. And in contrast to, for example, the merge sort, the items are swapped around in place. It doesn't create new, smaller lists. The partitions stay in the main list, so it doesn't create extra space in memory. But because of this big random factor that affects it, it can be slow sometimes. The speed will vary a lot, whereas merge sort is extremely reliable. Quicksort can be brilliant, but it can be slow. It's typically fast. It's got a good reputation with a lot of programmers, and many programmers use quicksort. And there are some modern improved alternatives, such as Tim's sort. They're not part of the course, but you will find programmers using quicksort as part of other routines. If you see some code and you're not sure if it's quicksort, what we'd be looking for would be two functions. And the second function is the partition function that partitions the list around a random value called the pivot, and what it will return to the main to the program is the pivot, the position of the pivot, because that is then the pivot at that point is in its final place. So those are some things that you might look out for to recognize a quicksort program. Quicksort and merge sort are the two fast sort algorithms that we learn on this course. So let me just briefly compare them to each other. Merge sort works by finding a midpoint, splitting the list into equal halves and using a merge function. Quicksort, instead of finding a midpoint, uses a random value called the pivot and partitions it in place to either side of the pivot. The merge sort is the faster and more reliable of the two, regularly coming in at n times log n operations, whereas quicksort varies a great deal, and on rare and unlucky occasions it can slow right down. On the other hand, merge sort does require additional RAM, whereas quicksort does not. So that's how I would compare the two. So in this short lesson, I've described how quicksort works and demonstrated it on an example, and we've discussed a few of the good and bad points and how it compares, particularly how it compares to merge sort. If you're my student, I've got a worksheet and we'll go through some quicksort programming lessons, but I'm going to leave quicksort now. You can find other people to describe how to do quicksort in Python, and I might come back and do one later, but for now I'm going to leave quicksort, and in my next lesson I'm just going to pull together everything we've learned about all 4 sort routines. And that'll be the end of this whole section on sorting. So bye for now.